Good day to the respected panel and advisors. I am Emerson Cruz Cumlat Jr., a Master of Engineering in Electronics Engineering student at Mapúa University. And today, I will be presenting my final defense titled Smart Optimization of Fiber Optic Network Design using the Prim-Dijkstra algorithm. Drawing from over 7 years of experience as a fiber network designer here in Fiji, this research addresses a real-world design challenge by applying algorithm-based solutions to improve efficiency in fiber optic deployment. This presentation is structured into 5 chapters following the paper's write-up. Let's proceed on the first chapter, the introduction. Fiber optic technology offers numerous benefits, including high bandwidth, reliability, and security. Key factors for modern applications like cloud computing, Internet of Things, and high definition media streaming. Conventional copper based networks, once adequate, now face challenges in supporting emerging technologies. The shift from copper infrastructure to fiber optic networks is driven by the demand for high bandwidth, reduced latency, and enhanced reliability. Despite its advantages, fiber optic deployment faces significant challenges, including high installation costs, complex infrastructure requirements, and geographical constraints. However, traditional network design methods often result in high costs and inefficiencies, necessitating the development of smart optimization strategies. As a fiber designer, we rely on manual and heuristic based planning, drawing from experience, predefined strategies, and practical judgment without the aid of automated tools. The need for cost-effective optimized solution in fiber optic network design arises from the necessity to minimize infrastructure cost while maximizing performance. Smart optimization methods help achieve this by utilizing advanced algorithms to reduce network deployment cost, improve resource utilization, and ensure scalability for future growth. During my research, I discovered two advanced algorithms, Prims and Dijkstra, that have yet to be applied to enhance fiber optic network design. This prompted me to explore these machine algorithms to achieve my goal of optimizing fiber optic network designs. Moreover, this study aligns with the United Nations Sustainable Development Goals, particularly SDG 9, the Industry, Innovation and Infrastructure, and SDG 11, Sustainable Cities and Communities. Enhanced fiber network deployment supports digital inclusion, economic growth, and the sustainable expansion of urban and rural infrastructure. This study centers on optimizing fiber network design in urban and semi-urban settings, where complex, dense node distributions present greater opportunities for improvement, unlike rural networks, which typically follows simpler and less optimizable paths. This is, the scope is limited to the optimization of existing fiber optic infrastructures and their enhancement through machine algorithms. We move to the second chapter, which is the review of related literature. A fiber optic network transmits data through optical fibers using light pulses. It is typically deployed in architectures like point-to-point or point-to-multipoint using passive components, meaning there are no electric devices between the transmission ends, only at the starting and receiving points. The implementation of a fiber network starts with the planning and design phase, which involves conducting site surveys, selecting an optimal topology, and obtaining required permits. This research specifically focuses on that initial stage, planning and design, prior to the physical deployment, installation, testing, and activation of the network. Fiber network topologies define the structural layout of fiber optic connections, influencing factors such as network reliability, scalability, and cost efficiency. Common topologies include point-to-point, star, ring, and mesh configurations, each offering unique advantages in terms of redundancy, cost, data flow, efficiency, and fault tolerance. Designing a large-scale fiber network requires a careful consideration of factors such as network topology, scalability, and redundancy to ensure long-term efficiency and reliability. Designers must also account for geographical constraints, budget limitations, and regulatory requirements to optimize deployment while minimizing cost and maximizing performance. One notable previous study on optimizing fiber optic network design is CommScope's fiber indexing approach, which simplifies a typical 240 homes distribution setup by replacing the traditional 20,000 foot star topology cable layout, where each terminal, the blue circles, serves 8 homes with a more efficient design. With fiber indexing, the total cable usage is significantly reduced. This technique utilizes a linear daisy chain topology, where terminals serve multiple functions. As a result, the total cable length decreases to 5,500 feet. Another ongoing research effort explores hybrid network design, which combines passive optical networks and active optical networks to optimize performance, scalability, and cost efficiency. AONs use a point-to-point connectivity that require more cabling and power, while PONs rely on unpowered splitters to serve multiple users from a central office, reducing energy use and overall deployment costs. Most existing studies on fiber optic network design addresses either cost reduction or performance improvement in isolation, underscoring the need for an integrated optimization approach, which this research aims to address using the proposed machine algorithms. My research conceptual model begins with the input, which is the initial fiber network plan. This plan will be processed using Dijkstra and Prim's algorithm. The resulting output will be an optimized fiber network design, which will we then evaluate and compare. This study targets key optimization parameters in fiber network design, such as cable length, deployment cost, and link loss, while preserving path redundancy, minimizing segments, hops, and pole usage, ensuring faster and cost-efficient deployment through algorithm improvements. Prim's algorithm is used to construct a minimum spanning tree by starting from any node and repeatedly adding the lowest cost connection to a node not yet in tree, avoiding loops and ensuring all points are connected at minimal total cost. In fiber optic networks, where nodes represent devices like switches and edges represent fiber links, weighted by factors like distance or cost. Prim's method effectively minimizes trenching cost by optimizing the layout for efficient and economical deployment. The flowchart outlines the process of starting with an initial node, adding it to the tree, and repeatedly selecting the smallest weight edge to connect to an unvisited node, an approach that can be implemented as a C++ program. Dijkstra's algorithm efficiently finds the shortest path between 2 points in a network by iteratively exploring connections and updating the shortest known distance to each node. This method is crucial for optimizing fiber optic networks, ensuring data travels the most effective route to minimize delays and enhance performance. The flowchart begins by assigning a distance of 0 to the source node and infinity to all others. Then repeatedly selects the node with the smallest tentative distance, updates its neighbors, and marks it as visited until all nodes are processed. This logical sequence can be translated into a C++ program. We move to the third chapter of this practicum research, which is the methodology. So this scenario presents the design and implementation of a cost-efficient and high-performance fiber optic network intended to connect 100 fiber access nodes for an internet service provider within the Pasig area, specifically covering barangays Maybunga and Rosario, serving approximately 1,600 households. The ISP may be a private entity or a local government unit. Each node functions as a fiber access point, delivering a high-speed internet up to 16 households. The primary objective here is to reduce the overall cost of fiber optic cable deployment while ensuring full node connectivity and optimized data transmissions route. To achieve this, a combination of Prim's minimum spanning tree algorithm and Dijkstra's shortest path algorithm is applied. This fiber network design follows a single line diagram starting from the optical line terminal, the OLT, and ending at the optical network terminal, the ONT in homes, with passive components like the optical distribution frame, the fiber distribution terminal, the access terminal box, and the network access point, including a 1:16 splitter, enabling the distribution of optical distribution signals to a 16 household without any active electronics in between. This illustrates how each network access point is individually connected to the optical line terminal. A tabletop survey was carried out utilizing Google Maps, Google Earth, and Google Street View to precisely identify the locations and assess the conditions of existing utility poles. The collected data was then digitized and used in AutoCAD for drafting and designing the fiber network layout. Key parameters obtained include cable distance, node positioning, splitter setup, and projected deployment costs. The Gantt chart presents a 13-week structured timeline for the Practicum research, covering literature review, data gathering, network design and optimization using the Prim's and Dijkstra algorithms, performance and cost analysis, final writing, and culminating in the defense presentation and manuscript submission, ensuring a systematic and efficient progression aligned with academic and practical goals. This is the visualization of a graph representing a region with 100 nodes. The total length of the vertices, which represents fiber cable length, is 15,648 meters. We represent the distance between nodes in a matrix format, which will serve as an input for our program. For instance, the distance between node 80 and node 81 is 109 units, shown in the matrix at row 82 and column CE, while a 0 in other cells indicates no direct connection between those nodes. This is the C++ script and program for Prim's algorithm. This represents the final program output with the data successfully exported into an Excel file format. Prim's algorithm is applied to the constructed graph to determine the minimum spanning tree. This algorithm identifies the subset of edges that connects all nodes with the minimum total weight, ensuring a cost-effective network, and the total vertices length after running the Prim's algorithm program is 10,433 meters. This is the C++ script and program for Dijkstra algorithm. This represents the final program output, with the data successfully exported into an Excel file format. This diagram illustrates the application of Dijkstra algorithm to the heuristic network design. Starting with all nodes distances set to infinity except the source node N0 at 0, the algorithm iteratively selects the node with the smallest tentative distance, updates its neighbors, and marks it as visited until all nodes are covered, resulting in a total fiber installation cost of 11,835 units based on the sum of the selected edge weights. Fiber optic cable and related accessories is one of the most expensive components in network deployment. Optimizing cable usage through efficient network design can significantly reduce overall project expenses. At a high level, estimate the cost of passive components, including fiber cables, ducts, splice joints, and installation, is approximately 400 pesos per meter. The estimated cost for electronics component, specifically the OLT, the optical line terminal, and the ONT, the optical network terminal, is approximately 200 pesos per meter of fiber deployment. We allocate 50 pesos per meter to cover project contingencies, management, and testing. This brings the total estimated cost per meter for the project to 650 pesos, which will be used as the basis for all cost calculations. The link loss formula calculates the total optical power loss in a fiber link by summing losses from fiber attenuation, splices, connectors, and splitters. The link loss calculation is derived from the heuristic-based design, taking the farthest node, node 87, relative to the OLT as the reference point. The total loss of 16.74 dB, accounting fiber length, splice points, connectors, and the splitter, remains well within the acceptable limit of 28 dB for a Class B plus optical system. Next chapter discusses the results and the expected output. As observed, the optimized optical fiber network design has significantly enhanced cable dimensioning by minimizing cable requirements and eliminating unnecessary routing, all while maintaining household coverage and preserving redundancy links between nodes. Heuristic designs often appear irregular with redundant paths. Prim's algorithm forms a loop-free, minimal-length tree. Dijkstra creates efficient, centralized path from the source, focusing on shortest routes. The route efficiency significantly improved with algorithmic optimization. Dijkstra achieved a 24.37% gain, and Prim reaches 33.33% compared to 0% efficiency in the heuristic design. In terms of link loss, at the worst case scenario, that is the furthest from the node from the OLT, the heuristic approach result is over 0.15 dB more loss than the optimized approach due to a longer fiber length. Both methods use the same number of components, splices, adapters, and splitters, but differ in total cable distance. By applying optimization algorithms like Prim's and Dijkstra, the overall fiber length is reduced, which decreases propagation delay and improves network responsiveness, especially in latency-sensitive applications. The algorithm reduces cable segments while maintaining a redundancy path, forming a ring topology that minimizes downtime in case of a fiber break. The cost of reduction analysis shows that applying the Prim's Dijkstra optimization significantly lowered overall deployment costs by minimizing cable lengths and unnecessary routes. The optimized fiber network designs using Dijkstra and Prim's algorithm significantly reduced the required poles compared to the heuristic approach. The table illustrates that as fiber cable length decreases through algorithm optimization from heuristic to Dijkstra to Prim's, the design and deployment times are significantly reduced, leading to a faster and more efficient fiber network implementation. We then move to our last chapter to discuss the summary and conclusion. Overall, while manual and heuristic-based planning remains relevant for smaller and or resource-limited projects, algorithm-based approaches provide superior efficiency, cost savings, and scalability. The integration of algorithm-driven methods are the preferred choice for large-scale and complex fiber deployments. The study faced challenges such as terrain constraints, cost variability, and limited scalability, with assumptions made on losses and a single case study without a real traffic data. Future fiber network planning should integrate real-world geographical information system, or GIS data, AI-based modeling, and hybrid optimization techniques to enhance accuracy, adaptability, and deployment efficiency. Additionally, validating simulated results through field trials, ensuring regulatory compliance, and training planners with user-friendly tools will support scalable and future-ready network designs. This study underscores the significance of graph theory in solving real-world infrastructures challenges and lays a foundation for future research and implementation in more complex and larger-scale network scenarios. The methodologies and results presented here can serve as a valuable reference for engineers and researchers working on the design and optimization of fiber optic and other types of networks. Thank you for listening and God bless.